So thank you, and let me also thank the organizers for the invitation to come here. Always a pleasure to come to ICTS, wonderful place. Okay, so the title of the talk is Correlation Coefficient and Representation Theory. It's all about finite groups today in this lecture. So I will introduce the notion. It's a very simple notion, and we'll do basically one example, and that's a talk. So the setting is as follows. Let G be a finite group. It could be compact, but today it's only finite groups. And suppose we have two subgroups. Let's call it H and K. So you have a big group G and two subgroups H and K. And you start with an irreducible representation of G. And this is classical setting, complex representation. So you have a big group G and a complex representation of the group. And we are going to assume that it has fixed vectors for the action of both the subgroups. So H has a fixed vector, K has a fixed vector. Moreover, only one fixed vector up to scalar multiplication. So the dimension of the space of H invariant vectors is 1. The dimension of the space of K invariant vectors is 1. So up to scalar multiplication, there is a unique H invariant vector and a unique K invariant vector. And because it's an irreducible representation, up to scalar multiplication, there is a unique G invariant inner product. So fix 1. Okay. So this is up to scalars 1. So I'm going to normalize that. Now that you have this inner product, chosen inner product, in the chosen inner product, you take the fixed vectors to be of norm 1. So fix 1 and normalize VH and VK so that they have norm 1 in this inner product. So now any two such VH differ by a scalar of absolute value 1. And the absolute value will not matter because whatever I'm going to define, I'm going to take an absolute value. So those things won't matter. Okay, so normalize VH and VK. So these are fixed vectors of unit norm. So this is the setting. And so in the maths literature, this came up in this article by Benedict Gross. So he defined the correlation coefficient of these two subgroups in the big group with respect to the chosen representation as the inner product that you have fixed, the angle between VH and VK, and take mod square. So this is the definition of the correlation coefficient. You're interested in understanding whether when you have two subgroups, the fixed vectors, what is the angle between them? In particular, they are orthogonal or not in that space. Okay, and one can easily check this is well defined. So in particular, VH and VK are orthogonal if the correlation coefficient is 0. Okay, so it's an easy to understand definition. And what is this talk about? So we are going to compute the correlation coefficient. We are trying to compute the correlation coefficient in one particular example. And the example is you take a finite field, FQ, and consider GL2 of FQ as your big group. And you need two subgroups. And these are two tori. The split tori, FQ star cross FQ star, and the non-split tori, which corresponds to a quadratic extension, multiplicative group of the quadratic extension, FQ square star. Okay, so FQ star cross FQ star and FQ square star. So these will be the subgroups. The short answer is that we are unable to do it in a proper way. And the rest of the talk, I will say what we are trying and what we can say. Okay. So all the pi's that will admit fixed vectors for this and this, we will consider the problem. So it's a finite group. There are finitely many representations, and admitting fixed vectors for either this or this, and in particular for both, will basically amount to the central character being trivial. So all the representations of PGL2FQ with the exception of 2, which I will list and get into this. Okay, so this could not have been my topic if that was the only answer that I could give. So however, there are some results. So remember, we started with the basic setting, a complex representation of G. So I would have liked to answer this without going outside that world, which I can't do. So there are some results, but in the mod P world. The question is complex, but the answer is in terms of mod P. That is to say, we do not know the value of C pi hk as we defined, but we can compute mod P value. Okay. So of course, this has to be made a bit more precise, and that will come a bit later. So I hope the setting is clear, and this is what we aim to do in this talk. Q is a power of P, so the prime P is given, which, by the way, I forgot to type, is not 2. Okay, everywhere I'll be inverting 2 later. So it's not 2, and P is any odd prime, and Q is any prime power, and then Q and Q square. So precise statements a bit later. So first, let me try to indicate what the difficulty is, at least in our approach, and then get to the real part. So the answers, of course, this is not the difficulty. This is part of the nature of the question, that the answer is bound to depend on how you embed the two subgroups. And so we are going to, so for the split torus, there is a more standard embedding, the diagonal torus. So we keep that and don't change that. And let's say FQ square is FQ root alpha. Alpha is some trace 0, root alpha is of trace 0. And then fix this embedding just to, start the talk. So x, y alpha, y x, all these things from FQ, and they are in GL2. And let's say K alpha as to be a model of the non-split torus. Yeah, it will depend on the, it depends on the embedding. So if you change the embedding, the answer. So just to illustrate the way the difficulty is, I'm fixing these two embeddings. And these two embeddings, one good thing about this is that two such embeddings of FQ square, I mean, instead of alpha, you could have taken another root beta, and then that will be just changing this beta, but exactly this one. They are same up to their conjugates by an element of H. And because of that, if you take only these kind of K alphas, then the correlation coefficient will be independent of alpha. Because any such thing will be, something from H and conjugate this group. And therefore, you will get independence of alpha. And therefore, I suppress alpha from this. Whenever I take this kind of K, I don't put the alpha, C pi hk to be this number. And let's do a small computation without going to mod P or anything, just in basic complex representation theory. So let's take what is called the principal series representation. So these correspond to two characters, chi1 and chi2 of FQ star, and then you parabolically induce. And in order to have fixed vectors, you need to assume that the product is trivial. So let me take chi inverse. Okay. So the vector space of this representation is given by all functions on G. G is GL2, two complex numbers, such that it's induced from the Borel, and because it's chi and chi inverse, I'm taking it PGL2, so the Borel is this. So on AB01G, it is chi of A, Fg, chi is the character of FQ star. So this is the space of pi. And using the Bruja decomposition, which is very explicit, it's just matrix multiplication for GL2, you can, so this will be a Q plus 1 dimensional vector space, right? And you can write down an explicit basis using this. So let's say Fg is 1 if G is identity and 0 otherwise as one vector. And depending on this double coset representatives, let's define for each lambda in FQ, F lambda of this to be 1 if lambda is mu and 0 otherwise. So you've got Q many elements here and 1 here. So these Q plus 1 vectors form a basis for a very natural basis for this representation space. And in this, it is a direct check to show one can, now that you have a concrete model, you can ask for concrete vectors, right, as a fixed vector. So in this particular model, one can write down VH. So VH, you can take those F lambdas, which were there at the bottom, and multiply by this factor. And as lambda varies over all non-zero numbers, one can check that this is H invariant, which is very easy to check. And this is also not difficult to check, not that easy, but you can write down this is K invariant. So you have explicitly got H invariant vector and K invariant vector. And we know this is a multiplicity one situation. At most one, this thing is, you have got up to scalars, and you can take the inner product and take the square, and that's the answer that you're looking for. So therefore you get so I'm normalizing by the orders. So C pi hk to be, I'm just taking the inner product of this. So this anyway, there's nothing there, and this times this with a bar will be chi of alpha minus lambda square by lambda. So that is alpha lambda inverse lambda, and I had a mod square. So this is the answer. So in terms of chi, you get an answer. So in any particular example, one can just compute it. One has a character, one knows the character. These are all some primitive roots of unity, and one can do the computation. So when you do this, you get different numbers, and there's no real pattern or anything. And it's not even, given this, one cannot even quickly say whether this is going to be 0 or not. So in that sense, it's not a satisfactory answer. Okay, so this is not easy to calculate in the sense, if you give me a Q and a particular representation, of course, either me or a computer can calculate, but as a theorem, this is not so good. From this formula, it's not obvious, yeah. In fact, if this was not there, it does depend. So it's a square that, yeah. Actually, maybe one can work it out because any other beta will be alpha times a square, and then one can plug that in and do something, and it should follow. But it's not obvious. So therefore, we approach the question. So this is where I'm going to introduce some mod P in order to have a nice result. So we approach the question sort of indirectly. To this end, I will do some very basic linear algebra. In some sense, I don't need to know anything other than a vector space has a basis, and given some linearly independent vectors, I can extend it to a basis. Basically, that's all that I need. Okay. So we start with some very elementary linear algebra. Recall again, this is the situation. So this is any finite group, any two subgroups, because what we are doing has nothing to do with GL2. So you have some finite group G and two subgroups H and K with this one dimensionality of fixed vectors for both. And recall that we fixed an inner product, and in that we normalized these to be of unit norm. And let me take the H average operator and the K average operator. So X is averaging over H, Y is averaging over K. Okay. So obviously, because it's H average, VH is X VH is VH itself because X is the H average. Any vector X will make it a H fixed vector because it's H average, and similarly Y VK is VK. What if you do the other way? You do X VK and Y VH. X VK will be a multiple of VH because X times anything will be H fixed. It could be 0. So it will be a multiple of VH where S could be 0. And similarly, YVH will be a multiple of VK. These two follow because of multiplicity 1, right? Any other vector will be a multiple. So you will get some numbers, S and T, two complex numbers, S and T. Now in the given inner product, you calculate VH comma VK. So VH is XVH. So it is this. And anything goes there as with an inverse, but you are averaging over everything. So X is self-adjoint. So this will be VH XVK, and XVK is what I called SVH. And it's a Hermitian inner product, so, and it's of unit norm. So what comes out is S bar. Let's do the same thing with VHVK applied Y, and the same thing, this time what comes out is T. So what we have got is S bar is equal to T. These two scalars, one is a conjugate of the other. And what was the definition of the correlation coefficient? Modulus of the square. So it is mod S square. It is S bar times T mod S square. So let's do this in one more way. So this is what I said. You start with these two elements, and VH could be VK also, in which case I have written down only one, and extend it to a basis, and in that you write these rank 1 operators. Rank 1 because of multiplicity 1. And so you just write down the corresponding matrices and take the product and take the trace. So from this product, it's clear that the trace is ST, which is exactly the correlation coefficient, right? And this is mod S square, and S was this, so this is exactly the correlation coefficient. So on the one hand, you got trace of xy. So correlation coefficient is nothing but take the projection to the H invariant vectors, take the projection to the Y invariant vectors, compose them, and take the trace. That is the correlation coefficient in general. On the other hand, trace of xy is x and y way explicit, H average and K average. So you compose and take the trace. But pi h times pi k is pi of hk, and trace of pi of hk is what we call the character of the representation. So on the other hand, trace of xy is just this. So in terms of the character table, we have got an identity for the correlation coefficient without really doing much work other than very basic linear algebra. So we have just proved that for an irreducible representation of G with one-dimensional space of invariant vectors H and K, the correlation coefficient is this double character sum. Double sum of characters. The identity is obviously true if there was no H fixed vector. Left hand side will be 0, and the projection to the 0 space will be 0. So right hand side will be 0. So this is true even if one of them or either of them does not have a fixed vector. So a consequence is if you assume you have at most one-dimensional fixed vectors, then you take the regular representation. In fact, in the lemma, I did not use irreducibility. I only used, it's a representation. So you take the regular representation. So this is a representation whose character is the cardinality of the group on identity element and 0 elsewhere, right? Everywhere else it's 0. So plug in that, and then you also know that regular representation is same as each representation comes dimension number of times. It is dimension pi chi pi. So when you plug in that particular lemma, on one side you will get dimension pi pi, and for pi you apply that lemma, so you get this correlation thing. And on right hand side you compute that character. So on identity you get cardinality of G, and everywhere else it's 0. And from that you will get this particular number. It is so if you vary pi through all the irreducibles and compute the correlation and put the weight dimension pi and sum it up, this is going to be the number. So this much has come more or less for free. And what is a consequence of this? Because when we started the question, we did not even know whether correlation could always be 0 or not. So now we can certainly say there is at least one representation for which it is non-zero, because the right-hand side is a non-zero number. Right? So it follows that there are irreducible representations of G for which C pi hk is non-zero. So whichever group you take, whichever two subgroups with this property you take, there is going to be at least one representation where VH and VK are not orthogonal. So this we are unable to compute in general. Now we are back to our example, GL2FQ, split torus, non-split torus. But we proved that this can be computed, and we compute it explicitly. So let me say how we do it. So, the first step is convert the problem into one of character theory of complex representation. This we already did. This was the elementary lemma. And the next is we formulate an analogous problem for mod P characters, mod P representations, and in terms of Brouwer characters. So one can, inner product doesn't make sense, but the H average and K average makes sense. And so we reinterpreted that inner product in terms of the scalar multiple that comes in when you apply H average or K average. And that number in terms of Brouwer characters, one can get a similar formula. So that will be the second step. And solving this analogous problem was easy. So earlier you got some kind of a character sum and one could not go ahead with that. But solving the analogous problem is easy because now you are in the PP situation. On the left-hand side, you have GL2FQ, where Q is a power of P. And on right-hand side, you have FP bar. So your representations are algebraic. You are in some sim powers. And there, doing fixed vectors and doing these computations is very easy. So solving the analogous problem is easy because the PP case is algebraic. And so the question is, you are given a complex representation. How do I go to the mod P world? So that requires the modular reduction of complex representations. And for GL2, FQ, only for GL2, but even for FQ, not just for FP, this is well understood. And this is the work of Fred Diamond from 2007. So this is the key new tool, relatively new ingredient to the whole game. In order to go to the mod P world, you want to understand the mod P reduction of representations, and that comes from diamond. So as I said, central character has to be trivial, otherwise there's no fixed vector. And therefore, you may as well focus on PGL2FQ, GL2FQ modded by the center, the scalar matrices. So let chi be a generator of the character group of FQ star, cyclic group. So let chi be a generator. And similarly for FQ square star, let's fix a generator, call it eta. And let me list all the irreducible representations of PGL to FQ. And these are all. There are two characters, one-dimensional representations. One is a trivial character and the other is of order 2, which is, you have fixed a generator and half the power of that. And then there are this there is the Steinberg representation and this particular twist. So these two representations. And then what I wrote down earlier, principal series. For each character to start with, there is associated principal series. So chi power r, chi power minus r, where r can vary from 1 to q minus 3 by 2. And then there are the cuspidal representations, which are associated to the quadratic extension. So we have fixed a generator here. And in terms of that, you can write down other characters. And for all of that, so I have used this notation. I have put an r plus 1 because stating the theorem is convenient that way. So you have these cuspidal representations here. How many are there? R can vary from 0 to q minus 3 by 2. So how many representations are there overall? 2 here, they are of dimension 1. 2 here, they are of dimension q, Steinberg. And q minus 3 by 2 here, they are of dimension, which we have already seen. It is q plus 1. And then the cuspidals are of dimension q minus 1, and they are q minus 1 by 2 of those, 0 to q minus 3. These are all. And then one knows, again from elementary character theory maybe, that except this one and this one, everything else has fixed vectors for both. So out of these many representations, so there are q plus 2 many representations here, q plus 2 many representations here, and other than this one, and this one, except for these two, all the others are admissible representations for our study. Okay, so Q many. So let me state the result, and this is joint work with Arindam Jana, and from 2022. We have to go do mod P reduction. So you fix an identification between C and QP bar, and write. So I have named my representations, and there is an R coming in the naming, right? I'm using this R. And for Steinberg, R is q minus 1 by 2, and trivial I'm not going to consider because trivial anyway, the answer is trivial. Okay, so this is the R that is coming in the theorem. I have fixed a generator and named these using that and this R. So that R, you write the periodic expansion. Okay, so write R as R0 plus R1P plus etc. up to, so what is M? It is Q is P power M, that M. Okay, so Q is a power of P, that is M. So for principal series and cuspidal, where this R plus 1 is important here, and I'm expanding R, and R is Q minus 1 by 2 for Steinberg, and it is just this. So I have got these RIs in the periodic expansion. RIs, of course, depend on the choice of the identification, and choice of you're fixing the generator also. Chi and eta are fixed in order for me to get these R. And this is the theorem. So the correlation coefficient. So now, because of this identification, it was a complex number. Okay, it's mod square, so it's a real number. And because of all the normalizations, it is a real number between 0 and 1. It's a positive real number between 0 and 1. But let's say it belongs to C. And because of this identification, it is in QP bar. But the point here is it belongs not just to ZP bar, but ZP itself. So reducing mod P itself makes sense, not just some prime ideal above P or something. So mod P makes sense, and modulo P, there's a nice answer. It is these binomial coefficients put together. So this is the answer if each of the Ri is even. If each one is even, not R is even, but each of the Ri is even. If any one of the Ri is odd, then they are orthogonal. No, they may not be orthogonal. The mod P value is orthogonal. There is some number, mod P, it is 0. Okay. So coming back to the old problem, this does not solve the original question, but it solves in some way, in one way, For example, by doing something, if I get something non-zero, I can at least say the original answer is non-zero, because mod P it's non-zero. Mod P, if it is zero, I cannot conclude anything about the original. But there is still some freedom because this is totally not canonical. Therefore, suppose I do this, and this is of course very easy to compute, binomial coefficients. Suppose I get zero. Change the identification, which will mean changing the generator of the cyclic group. And for that new R, I may get something non-zero, it's possible. Even if I get zero with, the chi that I started with or the eta I started with, change the generator, you may get non-zero, in which case you can conclude about the original question, answer is non-zero. So some flexibility is there, but anyway, regardless of the original question, mod P, there is a neat answer. E to the m is exactly Q. That's where it's stopping at m minus 1, yeah. Okay, so mod P, this is the answer. So in this situation, the vanishing of the correlation coefficient is closely related to the root number of pi. Root number is not a big deal here because it's just GL2 FQ. One can explicitly say what it is. It's a sign. It's going to be plus or minus 1 because PGL2, so self-dual. And when pi admits fixed vectors for both h and k, root number turns out to be plus or minus 1. And it is necessary that the root number is 1 for correlation to be non-zero. If correlation is non-zero, then the root number is plus 1. When Q is P, the condition is also sufficient, but not for P square, etc. Okay, so if for QP, not QP, for FP, if the root number is minus 1, then the correlation is 0. And the correlation meaning the correlation as a complex number, not just the mod P result. Okay. So roughly half the time the correlation vanishes because plus or minus 1 is roughly half. There are some exceptions to this thing because it's not sufficient in general, but roughly this is the situation. So just to recap whatever we have done, yeah. Robin.
It's not sufficient, as in you have any counterexample?
Oh yeah, many, yeah. Not many because roughly half the time I do say. So there is no counterexample for FP. But you can create counterexamples for FP square. So I'm not getting into that this talk, but that's also a very interesting story. The only counterexamples that we can produce is take something where the root number is minus 1 downstairs and then base change. And in the base change, the root number may turn out to be 1, but the root number minus 1 downstairs, that thing makes a correlation above 0. So it's something like, L half of base changes L half of pi times L half of another copy of pi, so to say. So root number being minus 1 at the ground level is enough for the L half to be 0, which makes this L 0. So such things happen, but I'm not getting into that here. Roughly half the time correlation vanishes, and for all this story, we took that particular embedding. For the non-split torus, especially, there could have been many other. Okay. Anyway, you can conjugate with any element and get all kinds of embeddings. It was important that we chose that particular embedding, which was at least independent of alpha. And of course, the answer does not depend on alpha, is clear here. There is no alpha here. Okay, so with the chosen embeddings, we are getting non-zeroness roughly half the time, and half the time it is 0, and that's the story, and that's all that I say about this. Now let me come to the second part of the talk, where I will motivate the talk by quoting this result of Ashay, Vehesh, Kobayashi, and Ota, where of course, the paper has many number theoretic things where they needed a technical result about representation theory of PGL2QP. And what they wanted was that the local new form, the new vector, is a test vector for so you are taking QP and the unramified quadratic extension. And with respect to that anisotropic torus, that non-split torus, the unramified torus, you take the toric period, and they had to show that the new form is a test vector. I mean, the toric period evaluated on the new form is non-zero. But that, of course, is not that difficult, but the novelty of the paper and the way they have to spend some time and some effort is that they can take an embedding of the unramified torus in such a way that it does not depend on the representation. In order to get non-zeroness of the new vector as a test vector, depending only on the conductor of the representation. So if you give me the conductor of the representation, I can fix an embedding so that for all the representations of that conductor, nu vector is a test vector. On the nu vector, the answer is non-zero. And that was important for them. And this is done for conductor greater than or equal to 3. Actually, I wrote greater than or equal to 3, but because it's coming from unramified, conductor is bound to be even, conductor has to be even. So what they have done is for 4, 6, 8, etc. All the even conductors starting from 4 onwards. Okay. Moreover, it is shown, and they stress that this is important for them, that this toric period is an L-adic unit for whatever L you give, which is not P, it's an L-adic unit. You can choose the embedding in such a way that it's an L-adic unit and works uniformly for all representations with a given conductor. So in light of this, it is natural to ask, and it's, Dipendra Prasad, who asked me this, pointing out this paper of Ashay, etc. In our situation, GL2FQ split and non-split tori. So in the work that we have done, you chose a particular embedding and half the time you got non-zero and half the time you got zero, right, for representations. So one can ask, so H anyway you fix a standard embedding. And can you change the embedding of K, conjugate the previous embedding in such a way that the correlation coefficient is non-vanishing simultaneously for all the representations? This will be mimicking that what they have got, right? So now you change the embedding. Earlier embedding was good for certain purposes. It captured the answer in terms of root number, etc. But if you want this question of getting non-zeroness simultaneously, then question is, can you take some other embedding of K such that the correlation is non-vanishing for all representations together? In order to, go to cuspidal for PGL to QP in the depth zero situation, getting it for all cuspidals is enough. But, there are only so many, so ask for all, right? It's even better. Moreover, because our machinery is only mod P, etc., it's not L not equal to P that one can naturally ask. One can go ahead and ask from, that aspect, can you also say that it's a p-adic unit? So these are natural questions inspired by that work. So with this in mind, we compute the correlation coefficient of pi. H, let us fix a standard diagonal torus and change K, conjugate it and make it not so nice as the earlier K. So by a suitable conjugate, so in Ashay's work, they conjugated by a standard unipotent elements 1U01. We will also try the same thing. Okay, so this is, so let U be in FQ such that K alpha is my previous embedding with which we had the previous result. And let us, conjugate it to make it not so nice. The earlier embedding was very nice. Answer did not depend on alpha, etc. Now, by doing this particular thing, it's going to depend not just alpha, of course, U also. So you are making it very dependent, but we have some other aim now, getting non-zero together. So earlier, the pair was carefully chosen in order for this to be independent of alpha. And in this case, roughly half the time, the correlation was zero. Whereas now, of course, we made the embedding kind of bad. And then therefore, the answer will depend on all possible things. And we expect it to depend on both U and alpha, and it will. So here is the result. We have this theorem. The techniques are the earlier techniques. So under any identification of C with QP bar, and writing pi is pi r, this is our earlier naming convention, that particular r, where 0 bit r between these two, depending on this identification, exactly as earlier. We have for this new embedding of K also, it belongs to ZP, exactly like earlier. Earlier it was, I just wrote K, which was the situation, U was 0, and then it became independent of alpha, and therefore I wrote just K. So now it depends on both this thing, ZP. And then what is the answer? So again, we have the answer only mod P, and this is the mod P result. So this is mod P, it is this number, and what is this number? So it is a certain polynomial evaluated on, so answer depends on U and alpha. It's evaluated on U by root alpha and the square of it. This is the answer of this modulo P, where P are the famous Legendre polynomials. Okay, so these classical polynomials which are studied all over mathematics. So I'm normalizing so that the standard way in which it's written, it's half integers are the coefficients, so it belongs to this. So pi r was my naming convention for. So I wrote Steinberg and then principal series chi power r, chi power minus r, and cuspidal as eta power something times r. So that r, because earlier the p-adic expansion of that r entered into the theorem. So there is that r in the naming. It's changing the identification, that r will change. Right? So it is the rth Legendre polynomial evaluated at u by root alpha. So everybody had to study Legendre's polynomial at some time, maybe in BSc or something, but I had forgotten, and some of you might have forgotten. Let me just copy paste from Wikipedia some of the basic points. It can be, it can be defined in various ways, and all those coincide. And it can be defined via a generating function. This is a generating function, 1 by root of 1 minus 2xt plus t square as summation prxtr. And one immediate corollary of this generating function, which can be seen from any definition in various ways, but easiest way may be this, which is that you take x to be 1. So when x is 1, this is 1 minus t whole square. So after root t, it is 1 minus t. So 1 by 1 minus t is 1 plus t square plus etc., which shows that PR evaluated at 1 as 1. Right? Summation t power r, this is. You can define it via a recursion formula. So this is a standard recursion. It's called Bonnet's recursion formula. The PR plus 1 times r plus 1 is 2r plus 1 multiplied by x, and subtract this and start with the initial points of p0 is 1 and p1 is x. PR of 0 is the previous result, it should be, which I will come back to. Yeah, it requires one more observation to show that this coincides with this. But good point. Since you mentioned this, if you put u equal to 0, then the dependence on alpha goes away. Right? PR of 0 is independent of alpha, so that's clear from here. But whether PR of 0 is exactly what I wrote down, I need to make one more observation, which I will. So, maybe the most standard textbook definition is via the solutions of this Legendre hypergeometric differential equation. So you solve this, you get it's a degree 2 differential equation. You have two classes of Legendre polynomials, first kind and second kind, and these are the first kind that come here. Okay, so there are many okay, another famous way is, you take the standard, of course, why am I telling all this? These are all there in BSc maybe. So 1x x square, you take the standard basis for the polynomials thing and apply Gram-Schmidt to that. What you get is under the natural inner product integral fg bar. F inner product g is fg bar, apply Gram-Schmidt to the standard basis, what you get is, so these are orthogonal polynomials.
How do you explain the
Came out.
just by calculation? Is there some?
That's how I got it, and I did not even realize these are Legendre polynomials for some time. But now that we have got it by literature search and various other ways, there are some explanations. Maybe I'll make some comments, free talk at the end. I think I will have time. So I'll come back to it. And I'll also refer to a famous talk online, which has all the much better explanations, not by me. So there are many explicit expressions of these polynomials. In fact, Wikipedia, that page itself has 7, 8, and there are so many. Many books, there will be many kinds of expressions. And we will write down 2 because in our proofs, either one is enough. So let's just say Sk is all the even integers up to k if k is even, and all the odd integers up to k if k is odd. And then this is one famous expression. Prx is 1 by 2 power r. These binomial coefficients x power I. So it's a polynomial of degree r. And here is another expression. So now it's not in terms of x, but in terms of 1 minus x square and x. And then these coefficients change a little bit. Normalization factor remains the same. And degree you can see is r minus I plus I r. Okay. So there are many other similar expressions, but let me state these 2. And I'm stating these 2 because now let's go back to the proof of the elementary lemma. Okay, just to motivate how these things come. So if you recall the proof of the elementary lemma, basically there were 2 things. One is the H average operator, which I called capital X, and then there was the y, capital Y, which was the k average operator. So if you have a new k, you take the corresponding operator, and those are the ones which are going to play a role. And then I call these two numbers S and T, and I played with that. And so basically, you can apply the H average on the k fixed vector, and that captures the correlation, right? If you got that number, it was mod square or something like that. So you can apply the H average on the k fixed vector. That will give you information about the correlation coefficient. Or dually, you could have applied the k average on the H fixed vector. Either one of those is enough to capture information about correlation. This was the content of the elementary lemma. So we could look at either the action of this average. Now I have this unipotent conjugated k. So either the action of this on VH I need to look at, or the action of H average on the fixed vector for k alpha u. These are the things that you should look at. So I could have proceeded using this approach or using this approach, and I quoted those two because if I proceed this way, this first polynomial emerges. And if I proceed the second way, the other polynomial emerges. Looking at this, it's not at all obvious these two are same. Of course, there are, I mean, one can just expand and do all these things, but it's not obvious. But here is a nice way of seeing that these two are same. One was, studying correlation using k average on H fixed vector. The other is what pops up when you do H average on the k fixed vector. So they do coincide. And one can also see, PR of 1 is 1 nicely from here. For example, from this, it's not at all obvious PR of 1 is 1, right? If you put x equal to 1, it's a certain sum. And this sum is 2 power r is not that obvious. Whereas now that you know these two are equal, PR of 1, if you take in this, x square is 1, so this is 0. So everything vanishes unless r equal to I, because this is 0, right? So PR of 1 is when I is r, and therefore you go and plug in I equal to r there. And when you plug in I equal to r there, it is 2 power r. It's 1. So one can do these things. So these respectively lead to the two expressions in the previous slide. That was the reason for my quoting exactly those two expressions. Either one would suffice for our purposes. We don't need both approaches. So the proof proceeds by doing Q equal to P first, as should be expected in the mod P world. Do P, and then how to go from P to P power M, because these polynomials have nice conjugants. Mod P, they have a nice conjugants thing. So this is what is called the Ilscher conjugants for Legendre polynomials. If R has this periodic expansion, then PR of X is PRI X power PI on this modulo P. So this is like the Steinberg tensor product theorem. And the most basic this thing which I learned from Shalini's thesis actually is the Leucard's, what is it called, Leucard's. So for binomial coefficient, if you have the periodic expansion, then the binomial coefficient is product of the corresponding binomial coefficients mod P. So this is a generalization of that. And Steinberg tensor product theorem is the representation theoretic analog. I don't know, because people do use representation. There is a way to use representation theory also to prove this. And in fact, this is there in a paper of Brzezinski. So it could be more than analog, I don't know. But let me just say analog, because it's clearly an analog. So, so that's how the proof works. And so I have not answered, yeah. 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 So let me just write that down. So this is all from Diamond, but let me just write down for Q equal to P, where the answer is easy to state. Otherwise, there will be all this, Jordan-Holder factors, too many. So Q equal to P, let me write down both principal series chi inverse and also the cuspidal. It came from eta. So this is Q plus 1. And when it is P, there are only two factors. So this pi. So pi has, so you take the sim power r of the standard representation, and it's central character 1. So you 2R and that minus R. So that makes the central character trivial. And this sits inside pi, and then the quotient will be some sim p minus 1 minus 2R p bar square, the corresponding. So that p minus 1 minus 2R. So this is q plus 1, this is 2R plus 1, this is p minus 2R, so it will be p plus 1. And for cuspidal, this is same, and here it becomes corresponding. So this is p minus 1R, right? This p minus 1, so this is p minus 3 minus 2. So so for when q becomes p power m, you will have to take all these Ri's in the p-adic expansion, and using all that, yeah, something similar. And the Jordan-Holder factors will be in terms of these things for each Ri's. So one can of course, a mod P reduction is only semi-simplification. Just the Jordan-Holder factors only one can write down, and one can write that down. Yeah. These exponents and the coefficient, these Ri's are coming in. This R is coming here. This R, right? 2R, this R. This was just P. I wrote only for Q equal to P. Otherwise, there will be Ri's and sim Ri's, and various things will come in the Jordan holder. No, that is mod L. L not equal to the cuspidals reduce, but Steinberg is irreducible. No, I thought this was always true. Yeah. Anyway, I'll take a look here. Yeah. Okay. Yeah. Not L, P. Okay. So the proof proceeds by doing the case QP first, and then using this conjugance to go to P power n. So I have not answered the question that we posed. Can you do an embedding so that simultaneously it's non-zero? I've only computed it using the Legendre polynomial. So the simultaneous, yeah, we have this statement. So simultaneous non-vanishing question will be a question about purely about this Legendre polynomials now, right? So what one will need is choose a U such that this is non-zero for all R. R varies from 0 to q minus 1 by 2. So the question is, can you choose U so that PR of U by root alpha is non-zero for all those R together? So in terms of, so by replacing U by root alpha by a variable, you write the Legendre polynomial, and then the question turns out to be, is there a C which is a non-square such that this is not a factor of all of any of those. So as m varies between 0 and q minus 1, this is q minus 1 by 2, you don't have this as a factor. This will be the answer to the simultaneous thing. I did many examples. There are plenty of such C, but somehow I don't have a proof of this. So, but in examples, and once I realized it's Legendre, doing computations were very easy because I didn't have to do anything. Just go to Wolfram because Legendre and all, part of numerical analysis packages, right? So just put in factorize, and you get all the factors. Everything was automated. Otherwise, I was doing by pen and paper. So when I did not know these polynomials were Legendre. So experimentally, it seems true, but I don't have a proof. So let me end with two remarks, and then I will also make a comment on Rajan's remarks. So if you start with, now, I will just go from complex to mod P because we know how to go and go back. So I will use the inner product notation even if there is not an inner product, because in the complex world there is an inner product and something similar can be done in the mod P world. So if you take, so this is the element with which we played. We shifted the embedding, and this goes here as the inverse of this. So what is the reflection of this if you plug in just this observation to all these things? In terms of Lejeune polynomials, you will get this well-known conjugates. Q minus 1 minus R and R are the same mod P, which is reflected here. Instead of getting the fixed vector here, so what I will do is I will just do all the calculations only on this, and I will say R is less than P minus 1 by 2, because otherwise you are doing this with this reverse. So one could have done it anyway. One sees all this even without seeing these things while starting the proof itself, but then everything falls down nicely because it's matching with this well-known conjugates, and that corresponds to this. So what is the meaning of this? In the way we did the proof, instead of changing the K embedding, I will be changing the H embedding. Fix that particular K, nice K that we started with, and change the H embedding by this unipotent element. Do all the computations. You will get this Legendre instead of this Legendre. So you will have this mod P conjugates. And because of this observation, now one can see that PR of 0 in any of those polynomials, if you put PR of 0, what you will get is R choose R by 2 square. So in order to get the previous result, all that you need is R choose R by 2 square is P minus 1 minus R, P minus 1 minus choose P minus 1 minus R by 2 square. Because the result with Arindam-Jena, both these things came, but mod P, they are the same because of this conjugates. Or one can compute it directly. So giving back the earlier result. So the earlier result was plugging in U equal to 0 in this result. Next remark is, now that we know Legendre has come this way, one goes back and checks, and of course Legendre is part of representation theory, and the standard way in which Legendre, and there are many other hypergeometric polynomials which also come in representation theory, which I was not aware of. So there are these Gegenbauer polynomials, which are vast generalization of these hypergeometric things. And whatever we do for PGL2, if one is doing something for SON, the compact SON, usual SON R, then those polynomials will come as matrix coefficients, etc. So the usual way in which special functions appear in representation theory is, so in the PGL2 R case, Brilinsky refers to the book of Dieudonné, but apparently the result is due to Vilenkin, so Vilenkin and Dieudonné. So I'm writing R instead of FP. Simar det minus R, that representation is, you look at the matrix coefficient, take any G and take V to be this. So I'm taking this on homogeneous polynomials in variables X and Y of degree 2R, and take the middle one, the nicest one, X power R, Y power R, and write down the matrix coefficient for this, GV, V, and this is the Legendre polynomial Rth1 evaluated at AD plus BC by AD minus BC. So this is how special functions come in representation theory typically. What we see in this talk is another way in which Legendre polynomial has come. So it was natural to ask, what if you club these two together? And just for curiosity, I tried this, use this one, this knowledge plus what our result, putting together you get an identity which relates the square of the Legendre polynomial, which is exactly the correlation coefficient. With, if you look at this, there is a transformation, and these are the Legendre polynomials. And what are these AIs? AIs are the coefficients of the Rth Legendre polynomial. So square of PR is, in PR, you take the coefficients and fix those coefficients and take all the PI, but now once, right? That's a square, and this is once, and vary over everything. And there is this kind of a functional equation. Maybe these things must be known because almost everything about Legendre things are known, but it's very difficult to see whether something is known or not because there is no English word to search for in these kind of things. So, but anyway, this functional equation, whether it's known or not, I have written, which seems new. It seems new, but this is the reflection of the classical way of Legendre's polynomial coming in representation theory, together with what we observe in terms of correlation coefficients. So, and one more comment I'll make, though I wrote in terms of R, the way I get this is actually using finite fields. Because what I have done is, this is for any matrix coefficient, right? And these things go for any field. This computation is purely formal. So this is true for FP also. And then, A, B, C, D, what do I choose? I choose each element of the non-split torus. So you will get something to substitute and average over K. You will get a certain sum. Because it's over finite fields, these sums can be done just using summation x power p minus 1 as x power I is 0. And then you will get some expression and then manipulate, and one sees that it fits into this. And the way you get all these binomial coefficients, you can see that these are mod p avatars of some other binomial coefficients. Pull it back, you get the identity over integers itself. Yeah, so this was the last slide. And your remark was, how do you explain Legendre coming? No real answer except that when Dipendra Prasad asked me the original question long back, he also told me about the Gross's paper. And he in particular told me there are these words that he has seen in his MSc physics, which are there in that paper, and which are these Wigner-Raka coefficients. And the Wigner-Raka coefficients from 1940s or 50s maybe in physics. So Gross explains that if you take correlation coefficient, so when he introduces, he also computes a certain correlation coefficient in that paper, which is for SO3 as the big group. And one subgroup is SO2, and the other subgroup is, big group is SO3 cross SO3 cross SO3. And one subgroup is SO3 embedded diagonally. And the other subgroup is SO2 cross SO2 cross SO2. And he gives the correlation coefficient. Again, half the times it is 0 for this particular, these are fixed embeddings. No, I mean, one is natural embeddings. SO3 is diagonal and each SO2 in the corresponding SO3. So here also half the times it is 0, and the other half, that non-zero value, comes in terms of certain binomial coefficients. So he does not give the computation, but he writes that down, and then he makes a comment that after a painful computation, one sees that these are the 3J symbols, which are one of the Wigner-Raka coefficients coming in quantum physics. So, so the special functions come in these kind of things. It's not, in hindsight, it's not surprising. And the other thing that I wanted to say is for more general, the way it's connected, and to Vilenkin's work has all kinds of special functions and how it comes. I have not seen the book, but there is this recent talk of Ashay Venkatesh online. This was his Alphonse lectures at Harvard, which was just 2-3 months ago, maybe 6 months ago. And 2 lectures. The first one was, the title is Wigner-Raka coefficients, but it is about correlation coefficient. And there are these 3J symbols and 6J symbols which come together, I mean, which come in physics. And his talk is mostly about the 6J symbol, not 3J. And 6J is, so from his talk, I realized I did not see it anywhere else. 6J corresponds to the correlation coefficient where G is SO3 cross SO3 12 times. And one subgroup H is SO3 cross SO3 4 times. And the other is SO3 cross SO3 6 times. These numbers 4, 6, and 12 correspond to, phases, etc., of the tetrahedron. So it's symmetries of the tetrahedron. And the point of Akshay is, so he has this in-progress work with Griffin Wong, who was a student of Boucher Go in Chicago. And what they are doing is so these are all compact groups and all, right? And one actually computes a fixed vector, and in a product, everything is explicit. The point of their work is to, do this not assuming compactness of the group. In fact, they will work with GL2 QP kind of thing, or SO over p-adic, and the correct generalization of the Wigner-Raka coefficients. So basically, just to quote him verbatim, roughly speaking, you have a G. Now it can be non-compact, p-adic, whatever, p-adic or R, whatever. and you have a G and you have an H and you have a K, and you will be looking at L2 G mod H and L2 G mod K, and corresponding to the pi given, there is a certain operator, and because of distinction on both sides, there is an operator between L2 G mod H and L2 G mod K, and it is the L2 kernel of this map that one is studying. So L2 kernel is G invariant, and on X comma Y, maybe you have to take it on the diagonal X comma X or something. And that is the interpretation of the correlation coefficient. And then he says, classically these things come as special functions, and the reference he gives is Vilenkin's magnum opus. Yeah.
Any questions?
AD plus BC? Yeah. Yeah. They could be, yeah. Yeah, could be, yeah. Or maybe some alternating thing or something.
Can one take two representations and then pair VH of one representation with
pi1 and pi2 of G, the big group, and
pair the vectors one against the other? Does it make sense in physics or somewhere?
If you take G and pi1 and pi2 of G, pi1 and pi2 of G,
have the coefficients one against the other. Square, you can take the square.
One can certainly ask the question, right? You have the inner, no, this inner product was on the space of pi, no? So if you have pi1 and pi2, you need to come up with an inner product. No, but then there will be nothing, no? Because I use the uniqueness of the inner product using irreducibility. But what makes sense is if you have G cross G and take pi1 tensor pi2,
right.
But then it boils down to this question. So the correlation for, on this comment, if you take the big group to be, so suppose you have GHK and you take the big group to be G cross G, and one subgroup to be G embedded diagonally, it captures some information on the original situation, and the other to be H cross K, right? Then the correlation with respect to this triple is related to the correlation with respect to this triple. I think it is a correlation for yeah, it's something very explicit, 1 by dimension pi times that correlation. Yeah, it's exactly 1 by dimension pi times that. This correlation is that correlation.
Okay, let's thank the speaker.
Thank you.